Hello and welcome back to Math Class in Session. It's great to be back. Let's do some trigonometry problems. Page 319, number 7. A building of height h is observed from 2 points P and Q that are 105 meters apart, as shown. So we're given this diagram, and we're asked to find the height of this building. The angles of elevation at P and Q are 40 and 32 respectively. Well, an angle of elevation is, for example, if you were standing at P and looking at the building, you would have to elevate your eyes 40 degrees. So elevating your eyes to look up, that's an angle of elevation. And the angles are 40 and 32 respectively. Calculate the height h to the nearest tenth of a meter. So we're given the diagram, we got to find the height of the building. Solution. I put this in a green box because it's a key. We need a side of a triangle of which h is a member. Now we see h here. H is a member of this triangle, but we don't have any sides. So we can't get h until we get one of these sides. Do you see how this side is shared by these two triangles? So let's give that side a name, say x. And let's figure out what x is. Okay, I'm tempted to try to use a sine law. So x over sine 32 equals 105 over sine of this angle up here. So we need to figure out this angle. Luckily, that's easy, because 40 and this angle right here have to add up to 180. That makes that 140. Now 100 plus 32 is 172, and that leaves 8 degrees to go up there. 8 degrees. Now I can say x over sine of an angle, so side over sine of the angle opposite it, equals a side 105 over the sine of the angle opposite that. This is a sine law application. Now to get x, it's simple algebra, multiply by sine 32. Take a calculator, and we have x is 399.8. Now that I know what x is, I have a side of a triangle of which h is a member. I satisfied the green box. Now it's just a matter of using SOHCAHTOA. Don't use a sine law in a right-angled triangle, although you can. It's unnecessary. Why not just say sine of 40 is opposite over hypotenuse? Sine of 40 is h over x, but we know what x is. We just figured that out. And now we can multiply through by 399.8. Take our calculator, and we have the height of the building, 257.0 meters. One might notice we did not have to climb the building with a long tape measure. All we had to do was observe the building from two different points, 105 meters apart. Another math problem, trigonometry. The Pont de Gard near Nîmes, France, is a Roman aqueduct. Aqueduct. Two words in one, aqua and duct, meaning water and pipe. Okay, an aqueduct. An observer in a hot air balloon some distance away from the aqueduct determines that the angle of depression to each end is 54 and 71 degrees respectively. The horizontal distance between the balloon and the aqueduct is 270 meters. Calculate the length of the aqueduct to the nearest tenth of a meter. To do this, we're going to need a diagram. Solution, draw a diagram. Now, a common mistake, see, I put B for balloon. The balloon is at this point. A common mistake is to put the balloon somewhere between A and C, over around in here. But it says very clearly from some distance away. So B is displaced over here somewhere. Now, it says the angles of depression to the ends are 54 and 71 respectively. So if you're in this hot air balloon looking straight across, the angle of depression to look down at C, how much you have to push down your eyes, is 54 degrees, and 71 to push down to see this angle, or to see this end. Notice 54 plus 17 is that 71 degrees. So that's where these numbers are coming from. That's why B is displaced over here. And then it says the horizontal distance between the balloon and the aqueduct is 270 meters. This is the horizontal distance between the end of the aqueduct and the balloon. It's 270 meters displaced over. So that's our diagram. And I think drawing the diagram is the hardest part. We need to find the length of the aqueduct. I called that x. Let's do some math. Well, I would like to go x over sine 17 equals something over sine c, but darn it, I don't have any sides. So we're going to need a side of a triangle of which x is a member. And once again, this side right here is shared by these two triangles. Let's give that side a name, call it, say, y. Now we can find out why because we can do some SOHCAHTOA in this right-angled triangle. Notice, 54 plus 17 is 71 degrees, so this angle right here must be the complement of that, 19 degrees, because these all add up to 90 now. Sine of 19 is opposite over hypotenuse. So right here, using this angle, I can say sine is opposite over hypotenuse, just doing SOHCAHTOA, and I've got y. That's pretty basic grade 10 trig. Now, in this configuration, sine 19 and y, they swap places. That's a good thing to remember about algebra. When you see a fraction and a value on the left side, the value on the left side and the denominator of the fraction can simply swap places. Taking a calculator, that tells me that y is 829.3. So this y we figured out. Now it's just a matter of trying to figure out this angle here so that I can say y over sine of that angle equals x over sine of 17. Now I can see right away that that angle must be 54 degrees because this is 54, so this is 54. Another way to get it is to say the complement of 19 is 71. The supplement of 71 makes this 180, so that would be 109. And 109 plus 17 is 126, and 180 subtract 26 is 54. So we could have got it that way too, or by the Z pattern. And now we can say, actually, let's start with the thing we want. X over sine 17 equals y over sine 54. We're doing a sine law, so x over sine of this angle equals y over sine of this angle. X over sine 17 equals y over sine 54, but I didn't say y. Y, we know what it is. It's 829.3. Multiplying by sine 17, taking a calculator, and we have the length of the aqueduct.